what do we understand, what we don't understand about present climate change issues. We will address energy issues as they relate to climate in next month's presentation. And the month after that, hopefully we will talk about paleoclimate and how that ties into this issue. So I think the first thing to start off with is there's really more than one view of climate change. And as we all know, it's unfortunately often rather politicized and controversial. And of course, what you generally hear in the common media presentations are what's termed there in the middle IPCC consensus, or sometimes catastrophic view, which basically says that natural causes of climate variations are important, but that human influences are more significant and dominated by the emissions of greenhouse gases, especially CO2, carbon dioxide. And the adverse impact of these gases on regional and global climate constitutes the primary climate issue.
现在用你破会贝尔的 WiFi。
对啊，
我说请不要，就是让大家用在听飞过的东西。
我也在听呢。
好。
I'm hearing somebody.
你也在听哦。你也可以开啊。
Please mute your computer. Thank you.
And then we have what would be sometimes called the skeptical view or natural view. And that was the idea that human influence on climate variability and change is minimal, and that natural causes dominate climate variations and changes on all time scales. And I'm sure that, you know, you guys have heard that view as well. There's also another view, which has sometimes become known as the lukewarmer view. I know that's not a very good biblical term, but nevertheless, that's often what it's called. And that is a view that gives a higher priority to natural causes of climate variations, but also recognizes that human influences are significant. But one difference in that is that it puts an emphasis on a variety of human inputs, not just greenhouse gases. So while greenhouse gases are important, things like land use, aerosols, atmospheric circulation, etc., are important. So this view says that human and natural influences on regional and global climate will continue to be of concern during the coming decades. And I would say that I'm probably, you know, I would have to say that I'm the most sympathetic probably with that view. But in the interest of full disclosure, I will say that while I do find myself involved in this issue quite a bit, in fact, I work with a number of climate scientists, I don't myself generally run climate models, although there are people around me that do in my work. I am involved in weather models, which are a similar animal, but a little bit different. So global climate models, or GCMs, are basically coarse-grained approximations of the climate system. So these systems, generally speaking, depending on the model you're using and the purpose it's being used for, the grid size is between about 50 to 300 kilometers in size. So that means that many of the smaller features of the climate system are not able to be directly modeled. They have to be parameterized or estimated. These models are very complex. They include features of the atmosphere, the ocean, the land surface, sea ice, glaciers, heat exchange, often between the ocean and the atmosphere and within the atmosphere and the ocean, moisture exchange, equations of physics, and also non-physics equations approximations for those things that we can't model at the proper scale. And, you know, part of the reason for that is if you increase the magnitude, you know, if you decrease the size of the grid scale, you dramatically increase the computational time involved. So even though we're using supercomputers in these cases, the computational demand is still quite great. And clouds and precipitation are one of the most challenging areas for parameterizations in climate models. And parameterizations is the term used sometimes for referring to the things that we have to estimate that we can't directly relate always to equations of physics. But to put it simply, climate models are useful tools for conducting scientific research to understand the climate system. Generally, as far as vertical, I mentioned that they have maybe 100 to 200 kilometer horizontal resolution most of the time, sometimes a little smaller or larger. They tend to have a 1 kilometer vertical resolution and a 30-minute time stamp. So there's also a resolution of time that you have to think about. And the information that I've seen says that if you double the resolution, you have to provide about 10 times the computing power. I actually have for many years had my office just down the hall from a supercomputer that's used quite a bit for climate modeling. It's one of the fastest in the world, but there are still limits to what you can do even with a supercomputer. All right.
Kevin, can I ask a question?
Sure.
Are these models like continually updated, or do they update themselves like an AI?
Well, no, they don't update themselves. There is a lot more work going on with AI, but basically since the beginning of the 90s, there have been these climate assessment reports, which come out about every 5 or 6 years. And so we are now on the 6th one, which just is in the process of coming out. Some of it's already out. And every time that they do another iteration of the climate report, they update models. There's generally, I would say, anywhere from about 40 to 100 different models that go into climate assessments. So it's a labor-intensive process for sure. I think AI is being very actively looked at now, and there are models out there now that are using AI, but I wouldn't say that our climate models are quite to the point of, doing it themselves. Probably a long way from that. And, what I want to convey with this slide is that there are actually a lot of different uses for climate models, and some of them are more useful than others. I think probably the best thing that climate models do is the sensitivity experiments. So this is where you purposely alter physical processes in a model to see how it changes the outcomes. And that's very useful because it helps you see what parameters in the climate are more important than others. You might find out that, changing this land cover surface over in this area only has maybe a 1% or a 0.1% change in the data, whereas something else might dramatically change, say the temperatures or the winds or something else you're trying to get out of the model. Models are also used for reproducing past climates, something that we'll talk about more hopefully in a couple of months. I think that's probably a little less useful than the sensitivity experiments, but still very useful. And I only say a little less useful because there are parts of past climates, while we know a lot about them from proxy data, which is something I'll talk about in a few months. We don't know everything about them. So there are some uncertainties introduced there. Of course, the big issue that comes out most of the time in the popular press is simulating future climates. And that gets complicated as well, because as I said, we have to parameterize some things. We can't describe things perfectly. Climate models are getting better at that. And, as they continue to improve, we'll see how things go. They are also used to attribute extreme weather events, things like heat waves and floods. And there again, it can be complicated because many of these extreme events are sometimes smaller than what the climate model can see because of its grid size. And remember also, I mentioned that precipitation and clouds were some of the most difficult parts of the model system. And of course, that is directly an impact on whether the model thinks you're having a heat wave or a flood. Regional climate models are often, in other words, downscaling the model for a specific region is often done, but this can increase the error because whatever errors are inherent in the larger model are also going to be inherent in the smaller model. Sometimes shrinking the resolution size does help. Other times it does not. And of course, the models are used for emission reduction policies and a social cost of carbon. And while in theory, you should be able to do that with the models, I think it gets to the point, by the time you get to that stage, you're dealing with so many degrees of freedom in the data that sometimes that can be a bit of a risky business. I'm not really suggesting that we don't use climate models, but what I'm suggesting is that we more honestly and openly report their strengths and their weaknesses. So no one model is superior to the others in everything. And this is one of the reasons that many different models are used. And generally in those climate assessment reports that I mentioned, you're essentially getting an ensemble of a large number of models. So if you want to think of it as an average, although that's not exactly correct. And forecast models, weather forecast models are easily evaluated against observations, but it's a little harder with a climate model. One thing that's often done with climate models is they they tune them to past data. So, for example, in the fourth assessment report, which was roughly 10 or 12 years ago, the models were tuned to match up with the 20th century climate data, all of the different models. But yet, if you look at those same models for their 21st century predictions, you see very different results. And this is part of the problem with the tuning process, because essentially what you're doing is, I don't really want to say fudging the data, but you're basically using the best information you have from observations to try to come up with a parameter to estimate the things that you can't model directly because of the model resolution. Stevens and Boney said that in 2015 that there is now ample evidence that an inadequate representation of clouds and moist convection, or more generally the coupling between atmospheric water and circulation, is the main limitation in current representations of the climate system. There are, and I want to mention a term called, if you may have heard this term, it's abbreviated ECS, but it's called equilibrium climate sensitivity. And so usually a weather model, or rather a climate model, is determined to have a certain ECS value. And basically what that means is if you double carbon dioxide or its equivalent from pre-industrial conditions, say in the mid 1800s, if you that value is about 280 parts per million. If you double that, which would be 560, then what kind of a change do you see in the global temperature, basically? So, and interestingly enough, the latest round of climate models, the CMIP6 models, as they're called, actually most of them seem to have greater sensitivity, climate sensitivity. In other words, they project even more warming, which is a little concerning because observational data does not seem to imply that. And I'll talk a little bit more about that a little later. Here, well, let me give you an example. So some of the many of the current round of global climate models have an ECS value of over 4 degrees C. In other words, if you double CO2, they're saying that the Earth overall would warm by more than 4 C. But yet, studies that have looked at observational data, for example, Frank Bossi in 2020 looked at 1998 to the mid 2010s, and from the data, he estimated the climate sensitivity based on observational data to be 1.72 C, which is, you know, less than half of the 4 C we're talking about from some of these models. And there's been other studies as well that have come up with a number similar to that, somewhere around 1.7 C for a doubling. And another problem that global climate models seem to have is to adequately simulate natural internal variability on decadal to century timescale. So there's a lot of climate patterns in the oceans that operate on scales of, say, 40 to 70 years. And those don't always get simulated very well. I'll talk a little more about those later as well. So just to give you an example of the discrepancies I'm talking about, the green, one thing that we need to think about here is when we're talking about global warming, we're usually, you know, CO2 is what people talk about all the time, but there's an assumed feedback from water vapor that's built into that. The idea being that if CO2 warms the atmosphere, then water vapor, which is actually the most important greenhouse gas in the atmosphere, is able to be in the atmosphere in a greater percentage, a greater amount, because the warmer the area is, the more water vapor it can hold. And that actually creates even more warming. So so you get this like feedback on top of the CO2. So this chart here is focusing on the tropics from 1979 to 2014 from more than 3 dozen models. And if the water vapor effect is as dramatic as it's anticipated, at the 100 to 200 millibar range in the upper troposphere, there should be a greater amount of warming. And we're not really seeing that warming. And I should explain, if you're not familiar with meteorology, meteorologists tend to characterize heights in the atmosphere by the air pressure at that level. So basically the 200 millibar level there is the top pressure level, is the top of the troposphere where most of the weather occurs. And that's the area where we should see more water vapor showing up, and we've basically not been seeing it. So the red bars there are models that model both the ocean and atmosphere together, and then the blue bars are ones that just kind of assume a ocean surface temperature, so they're less coupled between the ocean and atmosphere. And then the black line is the observed values, and you see that the red bars, especially there with the fully coupled models, are really out of range for the observed data. And you know, so here you have basically an observed data 1.7 C equilibrium climate sensitivity versus 3 C or more from these climate models here. Now, in fairness, I would say that if this data went up to about 2020, we might see a slight improvement in the models, because there was a couple of El Nino years after 2014 that warmed the Earth. Basically, when we have El Ninos, which is a shifting of warm water toward the Eastern Pacific, because there's less cloud cover in that situation, the Earth tends to be warmer. And when we have the opposite, La Nina, it tends to be cooler. But that really wouldn't change this data very much over the 40 or so year period we've got here. Another thing that is important to understand when you're looking at climate models is something called representative concentration pathways, or RCPs. So RCPs are named in sync with various radiative forcing targets for the year 2100 relative to 1750. So essentially, when you have global warming, you're assuming that there's a radiative imbalance in the atmosphere, that there's a heating being caused by greenhouse gases and other things. And so these RCPs are named by the watts per meter squared imbalance. So 2.6 watts per meter squared means there's a 2.6 watts per meter squared imbalance in the radiative forcing. And so in that scenario, you're saying that the radio forcing continues till about the year 2100 and then declines afterwards. And that's equivalent to raising the atmospheric CO2 concentration to about 490 parts per million. For comparison, it was 280 pre-industrial in the mid 1800s, and it's now about 410. Then there's an RCP 4.5 scenario, an RCP 6, and an RCP 8.5 scenario. And those correlate to 650, 850, and somewhere between 11 and 1400 parts per million CO2. A thing that's very important to point out here is that many of the more extreme scenarios that you see, the warnings that come out in the media about, this paper says, this is going to be the dire consequences if we don't do anything. Those are based on RCP 8.5 most of the time. And the real concern there is that really is a little bit deceptive, because RCP 8.5, although it's sometimes referred to as a business as usual scenario, it is really a scenario that is beyond any kind of realistic expectation of what might happen to emissions and the resulting climate that we might expect. So really, it's beyond anything that we would really expect to see. Really, if they want to use an extreme scenario, say a business as usual scenario, the RCP 6 is probably a little bit more realistic. Although in fairness, I think in the recent 6th round of the assessment reports, I think you're beginning to see that scientists and others are coming around to the reality that RCP 8.5 is not a good way to go when you're assessing climate in terms of potential hazards, future hazards. And, the question becomes, well, would we really see CO2 concentrations really go up that high to 800 to 1100 parts per million? A logistical forecast model by Murphy in 2019 suggests that a CO2 peak of around 587 parts per million at the South Pole and 654 at Mauna Loa in Hawaii by 2100. Now that is based on essentially looking at the curve of the increase of CO2 that we measure at those two places and knowing how curves like that behave. They expect essentially a peak by that time. Well, if that was the case, then you can see that that number really doesn't get you above the RCP 4.5 there, or thereabouts. And in the latest round of climate assessments, the RCP 8.5 was redefined to an even higher CO2. And I think that's part of that thing where people are starting to recognize that that's just a really unlikely scenario, and certainly not something that we should be basing our projections on, and especially in terms of our response. When reviewing climate change publications, always note the RCP scenario that was used. If you see RCP 8.5, in my opinion, that's just not going to happen. And I am much more interested in papers that I see that are using one of those other scenarios like RCP 4.5 and 6. And I do need to mention that in the latest round, the 6th round of climate assessments, they've actually modified the RCPs to be called something else, but I'm still using RCP here because that's really what you see in papers and in the media. You haven't really seen the new terms out that much yet. Okay, so what is a good climate metric? Although most of the 21st century climate change discussions focus on global average surface temperature, there is an important caveat. Not even 1% of the heat in the Earth's climate system is stored in the atmosphere. Almost all of it is stored in the oceans. So eventually, The atmosphere is just going to do what the ocean does. The ocean is really the driver of the climate. So it's the heat that builds up in the ocean that's ultimately going to drive the climate. Now, one problem we've had with this is that up until as late as, say, the late 90s, the best way we had to measure ocean temperature was, oftentimes people would be throwing buckets over the side of a ship and just measuring the temperature. And that's, not always the most accurate way to get a temperature. And also you're not getting a lot of information about temperature deeper in the ocean. So scientists built the Argo ocean buoy network in the early 2000s, and that's improved those measurements a great deal. There are now over 4,000 of those around the world, but still it's only been operating for about 17 years. We have a similar problem with surface air temperature. The best data comes from Europe and North America, and but that only really covers in any density, great density, the last 135 years. And, for other parts of the world, we really only have good data going back about maybe 65 years. This is why we have to use proxy data, climate proxies like tree rings and ice cores and other things, which are valuable. And I'll talk more about those in a couple of months. Surface temperature measurements can be influenced by a wide range of factors that are unrelated to greenhouse gas warming, such as their siting or how much urbanization is occurring around it, incomplete data, maybe the geographic location. If you're on a mountain or on a mountainside or near a lake or a river, all those things have an impact, and you have to take those into account. Over water, sea surface temperature measurements, they depend on shipboard measurements. I mentioned that already, and so thankfully we now have the buoys. Satellite data is of value to us as well, because we can get like temperatures of the upper troposphere, for example, but that only goes back to about 79. And the tree rings and ice cores and so on do not provide the precision, of instruments, and are often not available in a manner consistent with time or geography. So here's a map of the Argo array I was talking about. Now, the Argo array does give us a pretty good idea of what's going on in the ocean, but it is limited to the upper 2,000 meters of the ocean. And why is this important? Well, the average ocean
Can we go
depth.
back one slide real quick?
Sure.
Thanks.
And so what these buoys do is they periodically drop down as deep as 2,000 meters and take measurements all the way along the way. So it's a very valuable network. No question that this is going to, in the long term, is going to improve our climate measurements and our ability to monitor the climate. They already have, but we really need a few more decades of data would be nice.
Are they anchored in the ocean, or do they just float around?
I am not really sure how they kind of keep them where they belong, but they don't. My understanding is they basically stay where they are. But that's a good question. I really I don't really know what the propulsion system is or quite how that works to kind of keep them where they belong. So this is a vertical profile of the tropical ocean. And even though the Argos, you can see I've got the 2,000 meter level marked there where the Argos reach, but the average depth of the ocean is closer to 3,700 meters. And notice that in the top 1,000 meters is where all of your temperature change is. And once you get to that 2,000 meter level, basically the ocean temperature at depth is 4 degrees Celsius or 39 Fahrenheit, and even colder as you go deeper below that. So even in tropical regions, the deep ocean is very cold. And this is really a design feature of the Earth, because as the Earth heats up, whether it's, regardless of whether it's human caused or naturally caused or both, anywhere that ocean water upwells, and it does upwell in certain places. So for example, along the west coast of South America, that cold water, some of that cold water is reaching the surface, and it's not going to be 4C when it reaches the surface, but it's still going to be colder than the surface water, and that cools the climate. So, what you may not realize is, even if we had some let's say we had a catastrophic warming of 4C in this century, the ocean would take as much as 2,500 years to respond to that, because it takes about that long for all the all the currents in the ocean to completely circulate. So even if the climate warmed dramatically, there is a certain amount of buffering, quite a bit actually, that goes on from the ocean because of that cold upwelling water. Now, here's a chart showing the estimated global ocean temperatures over the last 130 years or so. And you can see the 1971 to 2000 average is the dotted line across there. And you definitely see warming. Now, the Argo data is only the line to the right of the green vertical line there. And what you see there is roughly about a 0.3C warming in the last 20 years or so, based on the Argo data. That equates to something like 150 terajoules of energy added to the ocean in terms of heat content. I'm sorry, what?
It certainly looks like cooling from 1880 to 1910. Is there any explanation for the cooling?
Well, really, I think that's probably the last gasps of what we call the Little Ice Age, which mostly affected the Northern Hemisphere. So really the 1800s was still in that period, and you could argue that really the period from, say, the 1400s to the 1800s on average, I mean, there were a lot of ups and downs in there, were cooler than just about any period in the last 6,000 years. So really the 1800s and earlier is an abnormally cool period. And I think you saw the last of that around 1910. I guess that's where my grandfather's stories come, about, walking to school 5 miles in the snow uphill both ways, because he was born around that time frame. But actually, and I was going to mention this later, but actually there was as much heat added to the ocean in the 1920s to the 1940s, and you see that there, especially around World War II, as there has been added in the last 30 years. And that earlier warming is something that a lot of the climate models have not simulated very well. And maybe part of the reason for that is that at least a significant portion of that early 20th century warming, we know that there, I don't know what I'm hearing there, but
Stuart, if you could mute your.
we know that a lot of that early 20th century warming was naturally caused, at least a significant portion of it. And that is something that, many climate models have had trouble with, some of those natural cycles. And then you also see more cooling there in the 1950s and 60s, really up into the 70s. It was about 77 or 8 where the current warming trend really got going again.
Kevin?
Yes.
I know we have all these buoys out there now, but where's this data coming from before that, like 1880 and 1900 and all those years? Where's this coming from?
Basically ships. And so, you know, I don't think that you need to throw out that data, but it's not going to be as precise as the more recent. In fact, the gray areas or blue areas you see on there kind of represent your margin of error, and you can see that that gets a lot better after the Argo comes along, or even after, you know, 1985 to some degree. We also have on land, but this is just in the U.S., the Climate Reference Network. So the National Oceanic and Atmospheric Administration wanted to create some sites that wouldn't be essentially bothered by urban sprawl and things that might change the data over time. And so they purposely put these sites in more rural areas, and they often have triplicate data. So they have multiple sensors of the same type, so that if something goes out, it can be replaced. I actually, at the time this was being set up, I actually worked with a NOAA division that was doing a lot of this and putting these up. And, you know, again, this is not global, but it does give us something for the US. It was established around the same time as Argo. So again, we have a rather short data period. So this shows the average temperature anomaly from the Climate Reference Network since about 2004. You could see here that maybe there is a slight positive trend in the data. There's not a really huge change there. But, you know, one thing that's interesting about the warming of the last 20 years, I pointed out to you a minute ago that, you know, we've had roughly 0.3 C in the ocean warming since the Argo was established about 20 years, almost 20 years ago. But yet in the atmosphere, we had a delay in that warming. You know, people used to talk about the pause. So from the abnormally warm year of 1998, which was caused by an El Nino, up to about, you know, 2013 or somewhere in there, there really wasn't any real change in the overall global temperature. And then after that, you did see the atmospheric warming kind of catch up somewhat to the ocean warming that we saw. Because remember, I said the atmosphere is going to eventually follow the ocean. But one paper pointed out recently that the warming of the last 20 years or so essentially has its cause in the change of clouds. In other words, there's been a decrease in the right types of cloud cover that have allowed more solar radiation to get through. And of course, low clouds are especially important for that. And they stated that the cloud changes can be caused by a decrease in aerosols by atmospheric warming due to natural causes, such as, which I'll explain in a minute, the Atlantic multi-decadal oscillation, the Pacific decadal oscillation. Those are natural oscillations. But it could be caused by anthropogenic warming due to CO2, or by a combination of all of these individual factors. So this warming seems to be more caused by a decrease in clouds than greenhouse gases, but we can't say for certain whether that decrease in cloud was caused by the changes in greenhouse gases or other man-made factors. Just that it wasn't directly related to the greenhouse gases.
Hey, Kevin, is there a one-to-one ratio of temperature changes between the ocean Argo temperature and the land CRN temperature, or it's exponential increase?
It does not appear. I mean, there's lags. There's delays. There's lags in the, like I said, the ocean warming. There wasn't a pause in the ocean warming from 2020, say from 2000 to 2020, but there was a bit of a pause in the atmospheric temperature for about 10 or 15 years, and then it kind of started back up along with the ocean. So the thing you'll see when you study anything with climate is the response is not always immediate. You know, you get a change in one system, it may get delayed because there's so many factors involved. So like, for example, with the atmosphere, you've got atmospheric circulation involved, and atmospheric circulation affects how air, or rather how heat is radiated to space. And so it could be that when the ocean was warming through the 2000s, whatever the atmospheric circulation patterns were, apparently they were conducive to expelling maybe some of that extra heat so that the atmosphere did not warm. But eventually, you know, it started to catch up.
But yes, but maybe I should break it down to two components in this question. So there's a delay, but have we observed that 0.3 degrees centigrade increase in atmospheric temperature or not so far from 2000?
Well, I think it would be close to that value, but it's not uniform across the globe. That's the thing, you know, that's the dangerous thing about using a, you know, people always talk in terms of the globe is warming this much, but your particular region may not have warmed at all. It may have warmed more, or it may have even cooled. There are parts of the world like, I think there's an area south of Greenland that's actually cooled in recent decades. But overall, I would say, yes, that's about right. If you look over, say, since the late 1800s to the present, there's been a surface warming of about 0.9 to 1 degree Celsius, which is pretty significant. Now, as I said, some of that warming before, say, 1950 probably would have happened anyway because the 1800s were cooler than normal. But another interesting thing to me is that if you look at the surface warming, say the 0.3 C warming of the last 20 years or so, if we assumed that that is going to happen over the next 80 years to 2100, that would be 1.2 C. So that would imply that from the late 1800s to 2100, you would have a warming of something like 2.2 C. So that's actually not all that far above that observationally based equilibrium climate sensitivity we talked about earlier. Over time, Argo, Climate Reference Network, and others will help reduce, you know, the error bars that we're dealing with. I didn't say much about the satellite record, but it's keeping a good eye on the upper tropospheric temperature, and that's is rather important when we start talking about water vapor, and I'll get back to that in a minute. So what I want to talk about now is kind of what are all the climate factors going into these temperature changes and other, you know, it's not just temperature changes, it's changes in precipitation, atmospheric circulation, a lot of different factors. So there's a lot more than CO2 involved in climate. And while I've got these here, these two columns divided into natural and human, realize that these influences, some of them go back and forth between both. So you have, you know, long-term natural influences like solar output and changes in Earth's orbit, its eccentricity, its tilt, its precession, which would be, you could think of as the timing of the seasons, interstellar dust. So one thing I'll talk about in a few months is that orbital dynamics caused the world to be about 1 degree C, especially in the northern hemisphere, warmer about 6,000 years ago. And that had an impact on monsoons and climate in the Middle East and Africa. And I think you'll find out then that even some biblical history. We have volcanic emissions. Volcanic emissions almost always cool the climate because they eject sulfides into the stratosphere in particular and reflect more solar radiation. So if you were around for Mount Pinatubo's eruption around 92 or 3, the world as a whole cooled by over a half a degree C the following year. In fact, I remember monitoring. I've been the person that keeps up with the climate data in Oak Ridge, Tennessee for several decades, and I remember that year following the eruption, we only had 8 days that summer that reached 90 degrees Fahrenheit, which the normal would be more like 35 or 40. So we had a much cooler summer that year. In the long term, the location of the continents and mountain building affects climate. You have processes, these affect things like how the atmosphere and the ocean transport heat around the globe, the atmospheric chemistry, the cloud cover, the surface reflectivity, which is generally called albedo, and also the amounts of water vapor and other greenhouse gases. So on the human side of things, we have greenhouse gases such as water vapor, carbon dioxide, methane, nitrous oxides, and others. Landscape change is important because it changes the albedo. Carbon soot, aerosol black carbon. So for example, carbon soot can lay on snow and change its reflectivity, and that affects the climate. There are other aerosol effects. They're probably too complicated to go into here, but aerosols actually play a very significant role in the atmosphere, and humans do significantly affect the amount of aerosols in the atmosphere. And they also affect many of the natural influences. And often when we're dealing with this issue, for simplicity, other factors besides CO2, their effect will be translated into as if they were CO2, and so CO2 concentration. But this doesn't always reflect reality because different chemicals have different resonance times in the atmosphere. For example, methane that's produced that's emitted into the atmosphere may hang around for 10 to 15 years before it decomposes into carbon dioxide. Carbon dioxide, however, can hang around for a century. So that's important to know the different resonance times, especially since, in the case of methane, that it's a more potent greenhouse gas than carbon dioxide. Chemicals interact with the ecosystem in very complex ways, and many climate influences such as land cover, land use effects, and aerosols really don't lend themselves well to being quantified in terms of a CO2 concentration. And even the different government bodies that deal with this issue define climate change in different ways. The Intergovernmental Panel on Climate Change, the IPCC, they include natural climate variability in their definition, whereas the United Nations does not. So when we're talking about the greenhouse effect, we got to understand that the greenhouse effect is a good thing. If we didn't have a greenhouse effect, the Earth's temperature would be about 0 Fahrenheit instead of an average of 59 Fahrenheit. And obviously it'd be very hard to support very much life at that temperature. Energy, because of greenhouse gases, energy bounces, if you will, between the atmosphere and the surface as much as 7 times before it escapes to space. So greenhouse gases essentially have the effect of re-radiating some of the energy that the Earth's surface reflects back toward the surface, and that allows the atmosphere to maintain a warmer temperature. But it's also important to realize, and I alluded to this a minute ago, atmospheric circulation is very important. The atmosphere is not just a static system that radiates heat. It's more like a boiling pot of water. So because of the heat that's being unequally distributed around the Earth, air is constantly moving around. Ocean currents are constantly moving around trying to equalize the heat content, and that process expels a lot of heat from the Earth as well. The atmosphere would be quite a bit hotter if it wasn't for these dynamic effects. Now, I've mentioned these a few times here, so there are several natural variations that occur at multiple time scales that are very important. And a few of the more important ones are the decadal sea surface temperature changes. One of these is called the Pacific Decadal Oscillation. And so that can either be in a warm phase or a cool phase. So, so the pattern you see there on the map to the right of the PDO and AMO there under decadal surface temperature, you can see how basically the orange and reds area are showing you areas that are above normal during one phase of the PDO and areas that are below normal, and then it will reverse. And these patterns, and then there's one in the Atlantic called the Atlantic multi-decadal oscillation, and these patterns will change and affect circulation patterns and cloud cover, and therefore affect temperature. So, you know, you might have a temperature change on the order of as much as half a degree C that you could attribute to these patterns. Now, so that means that if we have anthropogenic human-induced warming going on, then there's certain times or decades when these patterns are going to be enhancing the warming, and other times when they're going to be counteracting it. So right now, for example, we are in a warm phase of the Atlantic multi-decadal oscillation, which is probably aiding the warming that, say, occurred in the last 20 years. The AMO went into a warm phase about 1995, and it typically would stay in a warm phase for roughly 30 to 35 years. So probably that's going to go in a negative phase by 2030. And at least for several decades after that, it may actually counteract what, to a certain extent, maybe not fully, but counteract to at least some degree, whatever warming is occurring in the background. Now, most people are familiar with El Niños and La Niñas because they happen on much shorter intervals, and they're basically a simple way of describing them is a seesaw of the warm pool of water that's normally in the Western Pacific. Some of that gets transferred to the Eastern Pacific in an El Nino, and that has major impacts on tropical wind behavior, waves of subsurface warm and cold water. And, you know, it wouldn't be such a dramatic influence if the Pacific Ocean wasn't so large. It has a lot to do with that. Now, what about carbon dioxide? Everybody talks about carbon dioxide. Is it a linear? Is it linear or logarithmic? So carbon dioxide definitely is a positive feedback on the climate system. If you have more of it, you will have a certain amount of warming, but the question is, how much warming? Well, if it was just carbon dioxide by itself added to the atmosphere, if you doubled it from the pre-industrial to 560 parts per million, then which we might be up at that level by the year 2100, then you would only get a 1.1 C warming for a doubling. But yet, you know, we've already mentioned that most climate models say a lot more warming than that. So where is that coming from? Well, it's because they are assuming a significant water vapor feedback, which I will talk a little more about that in a minute. But the warming on CO2 is not linear, because essentially what you're doing as you add more CO2 to the atmosphere is you're blocking the ability of the atmosphere to radiate heat away into space. But once those atmospheric windows get filled up, the addition of more CO2 doesn't affect the blocking of that atmospheric window. So it's the effect of CO2 is logarithmic. So you see this mod-trans result chart here at the bottom of the page. You notice how under 100 parts per million of CO2, you get a dramatic increase in the effect of its blocking of the atmospheric window, so that more of the heat stays in the atmosphere. But you see how that curve gradually smooths out. So what I'm basically showing you there is the effect of going from like 280 to 390 or somewhere in there is the same as the effect of going from 390 to 560. So as the CO2 continues to increase, the impact of adding additional CO2 is not as great. But now some have noted that, you know, the ocean uptake of CO2 declines with warming, so that may balance out that factor roughly. So basically, we know that of the extra CO2 that's emitted to the atmosphere every year right now, roughly half of that gets absorbed by the ocean. So what I'm saying there is that as the ocean warms, its ability to take up more CO2 declines somewhat. So this may roughly balance out the fact that CO2 becomes less effective at further warming the atmosphere as we add more of it. And I'll say more about that at a later date, but it might be interesting to note that it appears that in some of the dinosaur eras, the CO2 concentration may have been up in the order of 1,500 to 2,000 parts per million, as opposed to the 410 that we have today. So I mentioned that there is an assumption of a significant water vapor feedback. Most climate models assume a water vapor feedback that would be as much as double or triple the 1C effect of doubling CO2. But there's a lot that we don't understand about the full relationship between the processes of precipitation and evaporation. You know, CO2 is fairly constant in the atmosphere. It does vary a bit, but I mean, if you go around the world and measure CO2, you're not going to get, you know, probably much more than a 3% difference in measurement overall. But with water vapor, that's not the case, because it's really what drives our weather, and it can be anywhere from about 0 to 4% by volume of the atmosphere. So it varies rather dramatically. Now, when we talk about water vapor feedbacks in terms of climate models, we're usually assuming something called constant relative humidity. The warmer the air is, the more water vapor it can hold. But by constant relative humidity, we're saying that it's holding the same percent versus the amount that it could hold. And this generally also assumes that the atmospheric circulation would stay the same. Maybe this is the reason why so many climate models seem to be overestimating climate warming. I've already mentioned that the ECS value is much lower when you base it on observational data versus climate model data. And so this chart here is from the 5th assessment report, and you can kind of, and so the gray bars basically represent the statistical ranges of expectation of warming. And you can see that it's really kind of hugging the lower end of the range rather than the upper end of the range. So why are climate models so often underestimating this? And it seems maybe to have to do with water vapor. So before I explain this chart, let me just read you something here. So a while back, I showed you a chart, and I pointed out to you that 100 to 200 millibar level layer, which is the top of the troposphere, a little above 30,000 feet altitude. So a 0.3 millimeter change in water, precipitable water, which is a way that we measure water vapor in the atmosphere, in that level has 280 times the greenhouse effect as if you added that same amount of water to the near surface layer. So what's really more important for global warming is if you get water vapor way up in the upper troposphere, as opposed so much to the surface. So as global temperature increased by 0.76 C from 1970 to 2019, the total precipitable water increased by 0.14 millimeters per decade. This does not imply a positive water vapor feedback. Accounting for the sensitivity of the outgoing radiation from the Earth, changes in the water vapors, different layers, the effective precipitable water had a small declining trend. So this may imply that water vapor did not have a large positive feedback on temperatures, contrary to the climate models. And this may be the reason that the climate models on average simulated global warming of the lower troposphere that's about 2 times what's been measured by satellites during that period. And this trend seems to have continued, although there is some evidence that the drying in the upper troposphere may have stopped in the last few years. So there's one paper I saw that by A. Tandon in 2021, very recent paper, said that evapotranspiration may have increased by 10% since 2000, and that this resulted in a 3% increase in precipitation and a 6% increase in runoff. So what that's also saying is that although the upper troposphere may not be moistening as fast as the climate models think it should, the hydrological cycle may be speeding up a little bit. But of course, water vapor affects cloud feedbacks. How much cloud cover do you have? And that's very important in terms of how much climate warming you're going to see. So in tropical regions, it's been shown that some models underestimate the negative feedback of clouds. In other words, the ability of clouds to reflect more solar radiation back into space by as much as 40%, and that they tended to overestimate the water vapor feedback by 25%. Now, this is just for the tropical region. And they suggested that over a 3-decade period, relative humidity decreased by 0.5% per decade. So that means we do not necessarily have constant relative humidity. And so the atmosphere may have experienced a slight drying as it warmed in the last 3 decades. So these findings suggest that while we do have a significant water vapor feedback, it may not be as significant as has been assumed. And, you know, this is still a problem that we're still figuring out, basically. Now, there is an effect of CO2 that I have noticed in my decades of taking care of the Oak Ridge, Tennessee climate data, but it's not the CO2 effect that is generally talked about in climate models. So in climate models, we're talking about the effect of CO2 and water vapor over the whole atmospheric column, essentially the ability of the Earth's atmosphere to radiate energy into space. But there's something called the boundary layer or the surface layer that meteorologists deal with. And that is, the best way to describe it is it's the layer of the atmosphere closest to the surface, next to the surface, that gets influenced by the surface. So what you have to understand about solar radiation is the atmosphere is pretty transparent to the shortwave radiation that the sun projects into it. So basically, for the most part, the energy that comes directly from the sun goes through the atmosphere and hits the Earth's surface. Then the Earth's surface, because it's a cooler temperature, re-radiates the energy at a longer wavelength. And at that longer wavelength, the atmosphere does absorb that energy. And so in most cases, the Earth's atmosphere is heated from the surface up, not from the top down, but from the bottom up. And at night, the Earth's surface radiates energy into space better than the atmosphere. So what happens is, so you see that chart picture on the bottom of the page there. In the daytime, because the sun is heating the air and mostly from the surface up, the warmest temperatures will be near the surface. So that red line represents a temperature profile. So you'll have the warmest temperatures at the surface getting cooler with altitude. But at night, the opposite happens. On a clear night, the surface of the Earth on a clear night without clouds interfering will radiate energy the best. And so it chills the air right near the surface. So you'll have the coolest temperatures near the surface, but warmer temperatures aloft. And so that creates what we call temperature inversion. Well, it turns out that more CO2 near the surface interferes with that temperature inversion, just like water vapor does. And it makes the drop in temperature at night weaker. And so what you'll see from that is an increase in nighttime low temperatures, but not an associated increase in daytime temperatures. And that's exactly what I have seen over the last 30 years looking at Oak Ridge data, is the nighttime temperatures have went up by a degree or two, but the daytime temperatures have barely changed at all in many cases. And that is a CO2 effect, but it's a local CO2 effect. It really doesn't affect the heat in the entire atmosphere. It's just a local effect near the surface. So that's probably one of the reasons also that we've seen some warming temperatures that are focused on nighttime minimums, but not on daytime maximums. So here's another way of looking at the boundary layer and the surface layer from a cross section. So in the daytime, because of the sun's heating, the green areas are all well mixed and the heat's getting dispersed from the surface on up. But at night, you have this temperature inversion that sets up and it isolates the surface from the layers above it.
Kevin, on your previous slide,
Yes.
I noticed that it says on the top graph, it says a clear sky. I'm assuming that clouds greatly change this dynamic here.
Yes, they reduce solar radiation in the daytime, making your temperatures cooler, but they also trap long wave radiation from the surface at night, so they make your minimum temperatures warmer. So yes, it's a completely different situation under a cloudy sky.
And so that's the conundrum, because clouds are rather unpredictable where they're gonna appear. And so how you measure that or predict it becomes pretty difficult.
Well, that's one thing that weather models and climate models do, and with a decent amount of accuracy. But even with weather models, even today, they've improved, probably 2 or 3-fold over the last 20 years. But it's still hard to get a really accurate forecast beyond about 6 or 7 days because of basically chaos theory. So basically what we're saying is that increased atmospheric CO2 and humidity create increased downward long wave radiation back to the surface, which increases the local surface temperature. But this is not representative of the overall atmosphere, and it's not the same thing as the CO2 caused warming we're normally talking about from a climate model. And in the daytime, the air is well mixed compared to night, and so this minimizes those effects. So this is really a redistribution of heat rather than a significant addition of heat. And I just mentioned about the clouds. And this phenomena I observed in Oak Ridge, it's true all over the eastern United States, basically in the last several decades. You probably don't see the effect quite as well in a western dry climate because of the fact that water vapor is also a greenhouse gas, and since you have very little water vapor, the CO2 effect is probably not as great as the water vapor would be. And I haven't really talked about urban heat islands up to now, but this is actually a very important human-caused effect of warming. It's local warming. It's not a greenhouse gas effect, but it's a human effect. Even in small cities, you can see, and this is because of all the asphalt and building materials that retain heat and then re-radiate that heat, or even at night. And so even for a small metropolitan area, you can have a 1 to 2 degrees C increase in temperature. But in some of the really large areas, like say Mexico City or Tokyo or London, it can be as much as 10 to 12 C. That's way more than what we're talking about in terms of warming from greenhouse gases, even from the more extreme scenarios. And these effects are often, they're not the same. I mean, they're affected by the background weather and climate. So, let's say you have a strong wind in the winter, the effect is going to be very small. But, if you're in the middle of a high pressure zone with no winds in the summer, you can have a really strong effect from an urban heat island. And this is caused by pavement and asphalt retaining heat more effectively than natural surfaces and re-radiating that heat even at night. These same surfaces prevent water from infiltrating the ground, so you have greater runoff. There's less vegetation, and vegetation, at least in lower latitudes, tends to cool the surface because there's moisture constantly being evaporated from trees and shrubs, and that process of evaporating the water takes energy out of the air and thus cools the temperature. But if you don't have that, then you'll get warmer conditions. This is why, for example, a lot of the clearing of the Amazonian rainforest has resulted in warmer temperatures in those areas. Urban areas also increase the surface roughness, which affects reduction in wind speed and changes wind direction. And this may change weather patterns, including where and when precipitation occurs. And those vegetation and surface roughness factors are also important in non-urban landscapes. So for example, this study is basically showing you that just the changes in land cover. So like, changing the Great Plains to mostly cropland and introducing irrigation can change the temperature by as much as 1 degree C or more, which is equal to the total warming that we've had since the mid-1800s. Smaller scale study in Nebraska showed that irrigated croplands are as much as 2.5 to 3 degrees Celsius cooler than they would otherwise be. So here's, you can see how rural land cover effects have changed. So this is 1938 to 1992 for forests, agriculture, grass, and wetland changes. And those, all of these things, all of these land covers have different reflectivities. So they reflect, they will change the amount of solar radiation that gets reflected back into space. And so in total, globally, this can have an effect on the Earth's temperature. I mentioned aerosols briefly already. Aerosols have a significant impact on the climate, not only on temperature, but with regard to precipitation, cloud cover, reflectivity, and other factors. And the important thing to remember here is that because they are unevenly distributed around the atmosphere, they can create temperature gradients that are 60 times stronger than the effects of well-mixed greenhouse gases in the atmosphere. So you can see from that chart there, so this is for 2007 to 11, but it's pretty representative of what you typically see. You can see that there's a significant amount of aerosol loading in the atmosphere around Southern Asia and Central and North Africa. The Southern Asia is from industry, but the what you see in Northern Africa is dust from the Sahara. So these effects can change temperature patterns and storm system patterns and the distribution of rainfall. So here's an example from China. So around mountains, you have mountain ranges, you have topographic wind flow patterns that form in the day and night. It's kind of like a sea breeze, a land breeze, sea breeze effect. So like, and those occur because of the differences in temperature. The ocean heats up and cools down more slowly than the land does. And those differences in temperature between day and night drive a pressure difference, which creates a wind flow either onshore or offshore. Well, you have the same sort of thing going on between valleys and mountains. In fact, I experienced that here in Tennessee where I live. So what this study was basically pointing out is that because of the huge increase in aerosols in the atmosphere in China, it has affected the rain formation, and this has weakened the circulations which create rainfall processes in some of those areas. The human release of aerosols have had a significant impact on the climate, not only on temperature, but also precipitation, cloud cover, and so on. Some recent work by B. Stevens in 2015 suggested that the negative radiative effects of aerosols may have been overestimated by climate models. So overall, aerosols have a cooling effect on the climate. But if they were overestimated, this implies that they may have slightly overestimated the atmospheric CO2 effect. So in reality, this effect may be slightly weaker than some models have suggested. I'm not going to go too much into this one because this can get down into the weeds, but basically what this is suggesting is that cloud aggregation is that because of the differences between, say, the ocean surface reflects energy versus a bright convective cloud like a thunderstorm complex, if the thunderstorms clump together more instead of being, say, scattered out across the ocean scape, then it can have an effect on the amount of energy that's reflected back into space from the sun. So it can create less heating of the atmosphere from the water vapor feedback, but there would also be a stronger, more rapid hydrological cycle that would result in wetter events in more specifically focused areas and larger dry areas in between. This is still an area that's still being studied and maybe not that well understood, but it's another effect that could change because it changes the albedo of the Earth's surface. So if we try to summarize all of this and say, what are the major warming factors, greenhouse gas and otherwise? And this is important to understand because, as I said, some of these factors are addressable on decadal timeframes via pollution controls due to their short residence times, and other factors like CO2. If CO2 hangs around the atmosphere for 100 years, then it might be a little harder to remove it than some other things like methane, for example. If you can reduce the emission of methane, it only hangs around for 10 to 15 years. So if you can reduce the emission of it, you're going to see a more rapid impact from that. But this is a very interesting chart because it's really showing you that while, yes, it is true that CO2 is probably the most important man-made influence, it's maybe not by much. It may be 26 to say maybe 30% of the issue. Methane is a close second. Shortwave albedo change, so we're talking about the Earth's reflectivity, is very important. Tropospheric ozone, that's a greenhouse gas. Ozone's good up in the stratosphere because it absorbs UV radiation, but it's not good down in the troposphere where we live. And it's a byproduct of transportation and industry. And we've actually learned a lot about how to keep it from forming in the atmosphere, or at least in the troposphere. Aerosol black carbon, I mentioned that it can lay on snow. That's the next one there. Solar influences, solar radiation input does change. I will mention that while the visible radiation from the sun does not change that much in solar cycles, the UV radiation changes quite a bit more than the visible. And I think that's probably where a lot of the impact is coming in, because it can affect cloud cover through its effects on the production of different things in the atmosphere. Semi-direct aerosol flex and how much snow and ice is on the surface. So it's crucial also to point out that regional effects can exceed these overall global factors.
Are there any negative effects for feedback that humans have? Is there anything so these are things we all do and we're trying to, reduce them. Are there things that we should encourage more human participation that have a negative effect?
Well, one thing that I did not put in the slide presentation because I didn't want to make it too long, but so I've already mentioned that aerosols have a negative feedback, but of course you don't want too many of them because they can be problems for pollutants, breathing, that kind of thing. But increasing the reflectivity of urban spaces, for example, there's I may be improper to call it a plastic film, but there's a film that was created by some folks about 5 years ago that has these little glass modules, almost microscopic embedded, that are designed to reflect energy back into space at a wavelength that goes through the atmospheric window. If you put these things on top of your building, it'll cool your building by 5 to 10 C.
Yeah, I've heard about the paint that will actually air condition your building just by painting it.
I don't know why those kinds of things aren't promoted more, because as you see there, shortwave albedo change is 14%. That could have a pretty significant effect, especially in urban areas. We'll talk a little more about that next month too, when we talk about energy, because there's a lot of misunderstanding, I think, about what goes on with energy production. Okay, so it's often talked about, you know, we really have a problem with sea level rise. You know, I heard Al Gore say back when he was doing The Inconvenient Truth that, well, you know, Greenland's going to melt and West Antarctica is going to melt and it's going to raise the sea level by, you know, 13 meters or whatever. And that's pretty significant. And, you know, technically speaking, he wasn't lying about that, but he made it sounded like the way it was presented that this was going to happen next month. And the truth is, it would take about 2,000 years for the Greenland ice sheet to totally melt, even in like the worst case scenario, which that's not likely to happen. But having said that, sea level is very sensitive to changes in global temperature. We know that from paleoclimate studies. So, you know, we are currently in the warm period called the Holocene, which has lasted for roughly the last 10, 11,000 years. But you know, the majority of the time over the last few million years, we've been in the glacial cycle of an ice age in which the temperature was quite variable, but much cooler than today. And the last warm period was from roughly 130,000 to 115,000 years ago, and it was called the Eemian period. And during that period, there was I'd say about 2,000 to 3,000 year period, roughly around 120,000 years ago, where the global temperatures were as much as 2 degrees Celsius warmer than today. So we can look at that to kind of estimate to some degree what might happen now if that happened. And we see that sea levels were as much as 5 or 6 meters above the present level. So it is basically 20 feet. And that's, you know, that's significant. And even as recently as 2000 BC, they may have been 1 meter higher in some parts of the world, because in that mid-Holocene period, about 6,000 years ago, the Earth, because it affected the extremes of the seasons, there was a little bit less glacial ice and therefore a little bit higher sea level. So sea level over, you know, periods of millennia can change really dramatically. At the peak of the last ice age 20,000 years ago, the sea level was 400 feet lower than today. So like Florida, for example, was twice as wide as it is now. The thing about this, I think probably, in my opinion, the sea level is one of the most serious issues related to changes in the Earth's temperature. But at the same time, you need to understand that this is not something that's going to happen, you know, over a period of 10 years or something. We've made ourselves more vulnerable to this because of our fondness to build so much infrastructure on the coastline. I mean, really.
It was really delicious. Thank you.
I mean, I love everybody.
Yeah,
loves
there were enough. Yeah.
But the
it wasn't up to suicide level. But I enjoyed it. Thank you. Was that from the place that we've gone to before, or was it a different place?
Mark, I think you need to mute your microphone, please.
Okay, so right now the sea level rise is about, it's been really rising since at least the beginning of the 20th century. The 20th century average was 1.8 millimeters per year. At present, it's about 3.24 millimeters per year, which amounts to 15 inches per century. The fifth climate assessment report projected anywhere from 1 to 3 feet by 2100. You know, I think that 15 inches is a pretty good estimate. There are a few things that could affect this. One thing that people are concerned about are some glaciers in West Antarctica particularly the Thwaites Glacier, which is a very large glacial area that's basically blocked by an ice shelf that's melting away. And if the Thwaites Glacier completely failed, then it would raise sea level by a couple of feet. I actually tried to find out, I looked into some reports to see if we have a history of what the Thwaites Glacier did during the Eemian period, because it, you know, that would be a pretty good analog for what we might expect. And it looks like in order for that to happen, the Southern Ocean near Antarctica is going to have to warm by about possibly as much as 2 degrees Celsius. That could take a while to happen. So I don't really, you know, I think it's definitely, I'm glad people are concerned about it and they are looking at it. But I think, you know, if I was, you know, taking bets on it, it's going to be a while before that would actually contribute significantly to sea level rise. So I think, you know, most likely we're looking at 15 inches of rise this century, maybe 18 inches on the high end. That's significant, but it's not, you know, anything like, you know, the 6 or 7 meters from Greenland melting. And sorry, I'm mixing my metric and English systems here. So the bottom line with sea level rise is long-term land use planning really is needed so that we don't build infrastructure in a place that it's in danger. And it does take very little climate variation to have a change of a few meters in sea level. We know this from, you know, we have long histories from paleo data of the sea level rise and fall. But the bottom line is it's going to take a long time for it to rise noticeably. It's, you know, you're looking more at century time scales. So in summary, I would say that climate change is real. It's always been going on, but we are also having a significant impact on it right now. But it's likely more complex. There's more factors involved than just CO2, and it's somewhat more subdued than estimated by many climate models. You know, observations so far suggest the lower portion of the IPCC estimates. I mentioned already the 0.3C rise in, say, roughly the first 2 decades of this century. I don't really see a reason or way for that trend to dramatically change. It may be less or more slightly in different decades, depending on the effects of natural oscillations like the PDO and the AMO. But that basically gives you another 1.2C by the end of this century. Although climate change may be more muted than some claim, it is also more complex. And that is somewhere, this is somewhat countered though by the potentially large increases in energy usage expected from a growing global population. So this is something we'll have to talk about next month. We really couldn't do it justice today. I would love to see a reduction in politics. I think everybody knows this, but as someone who has done climate research, it's much more difficult. It's an order of magnitude more difficult to do research when the subject is politicized. This is certainly not true in every area of science, but it certainly seems to be in climate science. Because regardless of where you come down on the issue, having different points of view sharpens and improves everybody's data and results. It's just the way science works. And the current environment we have, I don't think really lends itself to rapid progress. Much of the focus on climate change might be better directed toward energy innovation with climate in mind, next month's topic. And although CO2 and other greenhouse gases are not an insignificant part of this issue, other factors like urban heat islands, land use change, aerosols, and even CO2 related temperature inversion reductions represent factors that are as much and sometimes more important than the general greenhouse warming. I think more focus on mitigating these factors may be quite beneficial. And I don't even know what time it is or how much time we have left, but I'll be happy to answer questions.
We now allow some question time. I have a question for you. On the media, regularly they contribute the hurricanes, the extreme weather pattern that we experienced within the last 5 years to climate change. What is your opinion on that?
While it is possible there could be some effect from that in the future, at least up to this point, I see no evidence of any clear signal from global warming and hurricanes. If you actually plot, there are roughly around, they go by different names around the world, but there are roughly about 90 hurricanes or tropical cyclones in the world every year, give or take about 10%. That average really has not changed in the observable record, which goes back 100+ years. And truthfully, we probably missed some storms back in the early days because we didn't have satellites, but some papers that I have seen on that topic suggest that the effects might be different in different ocean basins. So in some parts of the world, you may have an increase in storms, and other parts you have a decrease, and you have a shifting of tracks, storm tracks in some areas, which affects, who gets hit. But the overall global impact would be about the same. So, depending on whether you lived in the Atlantic region or the Western Pacific or Indian Ocean or whatever, it may be different a little bit, but so far there's not any real clear evidence of that. It's very, but see, this is an example of it being politicized, because we've always had disasters. We've always had one chart that I probably should have put in here, but if you look at a chart of deaths from natural disasters, and that would include things like hurricanes, but also many other natural disasters, there has been a huge dramatic decline in deaths over the last 100 or so years. And the reason for that is technology, because technology gives us the ability to protect ourselves better against many of these things.
Thank you, Kevin.
Kevin, everybody, discusses all the negative effects of global warming. Are there any positive effects?
Well, yes, I would not want to take the world back to, given that we have what, 7 or 8 billion people in the world now to feed. I would not want to take the world back to the 280 parts per million carbon dioxide, all the way back to that we had in 1850, because that has a negative impact on vegetation. And there's no question that at least in the last, say, 75 years, there's been a dramatic greening of the earth because of the higher carbon dioxide levels. So that implies something about crop yields. And I'm not sure that we could feed the world at the original CO2 level we had 150 or 200 years ago.
Yeah, that's been my thought for quite some time. And there might even be some other, a northern passage that they always wanted it.
Yeah.
Kevin, I have a question regarding the immediate impacts of things like, we had forest fires, which produced a lot of CO2, but it also put out a lot more aerosols and particulates into the atmosphere.
Sure.
As I looked at the Mauna Loa data, I didn't really see any blips in that. And as well as when we were all on lockdown and people weren't driving. And so I didn't, maybe the scale wasn't there for me to see that. Is there any reports on that, or?
Well, the Mauna Loa is, I believe you maybe are talking about all the forest fires or all the fires in Australia a year or so ago.
Well, even on the West Coast, we had all summer, this last summer, we had large, huge fires bigger than, we had millions and millions of acres in,
And about 94% of that in California is attributed to land management practices rather than climate change. Because of, for example, before humans were involved, you had natural forest fires that thinned the timber and thinned the underbrush. And, we had a policy for about 75 years of fire prevention where it just built up all of this extra kindling, basically.
Yeah.
We saw a dramatic example of this in East Tennessee about 5 years ago. We're not normally a forest fire region because, we're a pretty wet climate. I mean, we get over 50 inches of rain a year. But in the Great Smoky Mountains, Gatlinburg area, about at the end of 2016, fire prevention started in the 1930s. And there was so much of it built up that when a fire got started under the right weather conditions, and we had the winds at that time to drive it, it was devastating. And but it's I have a professor friend who's a dendrochronologist, tree ring expert, and he showed quite conclusively that this problem started because in the 1930s they started preventing all the fires from happening, and so all the underbrush started building up. And so when it finally goes, and that's really what, for the most part, that's what was happening in California as well.
But that's not, I guess I didn't clarify. I was wondering if any of the data as far as the impact of the release of CO2 has caused concerns, or is it measurable? And
I would say that in the general scope of things, it probably didn't have a huge impact. So like, because of the way atmospheric circulation goes, it would have had to basically went all the way around the world and then hit Mauna Loa. So by the time it gets to Mauna Loa, it's all, well mixed. So yeah, it's and as far as the Australian fires, they did have some impacts on climate in the southern hemisphere, but because both hemispheres kind of operate independently, it's not likely you would get the smoke coming across the equator to hit Mauna Loa. I think there was one other thing I was going to mention about that, but as far as the lockdowns and the pandemic, there you can show a demonstrable reduction in emissions in 2020, and it's not a huge decline, but it's definitely measurable.
Hey, Kevin, I have a question.
Yes.
Actually, two questions. This is Ben Clifton from Portland. When Hugh Ross was on Justin Brierley's show, he made a comment that I'd like your opinion on.
Okay.
And I'm not sure I understood him correctly, but basically what I understood him to say was that the longer term effect of the global warming that comes from the increase in greenhouse gases will actually paradoxically result in a cooling trend, because the higher temperature of the atmosphere is going to allow for more water vapor, which is going to result in more precipitation, which is going to result in greater snowfall in the northern hemispheres in particular. And that's going to result in greater reflectivity of the vast continental places in the northern hemisphere, which is then going to result in less energy absorption because of that greater reflectivity. So my question there is, just generally speaking, is that correct? My second question, and again, maybe just a general comment, is what is your opinion on, if you've had a chance to read Katharine Hayhoe's book, Saving Us, because she's another influential voice in this whole thing, and she does present herself as a, evangelical Christian. So those are my two questions.
Well, I guess I'll answer the second one first. I believe I read her prior book to that, one of her earlier books, and I can't speak to the more recent book, but the earlier book, and it's nothing personal against her, but just in reading the book, I honestly was a little put off by it because it felt like I was reading the IPCC standard line on everything with sort of a Christian veneer over it. And I hope that doesn't sound too harsh, but that's kind of what it felt like. And my criticism of that was, you're not answering the objections, the questions people have. It was just sort of spouting the official line, and it's like, I guess that's okay if that's her opinion, but why doesn't she answer some of the actual, credible questions? And there are credible questions out there that needed to be answered. And I think I would have been much more impressed with the book. Now, having said that, I haven't read the book you mentioned, and she may have done that. So, I'll just leave it at that. But as far as Hugh's comment, I generally agree with it, because what you've got to realize is, let's take humans out of the equation for the moment and say that we have no influence on the climate. All things being equal, we're only about, based on past cycles and looking at the patterns of different greenhouse gases and orbital dynamics, we know that we're really probably only 1,200 years away from the next glacial inception. While it is possible that our influence may prevent that for some time, we have to realize that the tilt of the Earth is declining slightly for the next 10,000 years. The tilt is not the only driver of glacial cycles, but it's one of the most important ones. And essentially when the tilt is, so the Earth's tilt ranges from about 21.5 to 24.5 degrees. Right now it's 23.4. As it declines, it protects the polar regions a little bit more from the more direct solar radiation. Doesn't sound like a lot, but it's enough to make a difference. And that's going to be happening for 10,000 years. And I have a hard time believing that even with our injection of greenhouse gases, that we're going to be able to prevent the next glacial episode, with 10,000 years of tilt changes and other things working against us. We might hold it off for some thousands of years. There is some debate about it. I mean, there are people out there in the climate community that say, oh no, we've prevented the next ice age and it's going to be warm for the next 50,000 years. Well, I just have a hard time accepting that. It's, because there's a lot of warm interglacial cycles that we can look at in the past, where even ones like the Eemian that had periods that were warmer than today, and still the glacial inception occurred. So I would definitely take my bets with Hugh on that one, that yes, we're going to have a glacial cycle at some point, even though we might delay it a little bit.
Thank you. Okay, we have another question.
Yeah, Kevin, on the subject of trees, what do you think about efforts like in Israel? They're trying to reclaim desert by planting trees around the edges and so on. What do you think about that if it were done, say, for the whole Sahara, to start doing that? Would that help the situation much?
It could help quite a bit. I mean, if you look at the, I'll talk about this more in a few months, but if you look at a map of the Sahara 6,000 years ago, because the Earth was tilting more then, the monsoons that moved north and south with the seasons went further north during the Northern Hemisphere summer. And so most of the Sahara then was a grassland with lakes and a few scattered trees, and there were people living all over it. And I mean, there was still some desert area, but it was not even 50% of what it is now. And actually it was when that changed roughly 3,000 plus years ago that people started to settle and create the great civilizations like Egypt and Mesopotamia. You know, there were a lot of people that were hunter gatherers in the Sahara and Middle East before that they did that because it was profitable to do that. But yes, you can artificially do that. Israel has, to an extent, I mean, Israel has done a great job with that. I mean, if you look at what Israel was like 150 years ago versus today, they have reclaimed a lot of area that, you know, made it into usable land.
Thank you.
Okay, I want to thank Kevin Birdwell, give us such a comprehensive explanation of the climate change. There's still a lot to learn, and I welcome everybody to come back again for next month, the same Saturday at the same time that Kevin is going to talk to us about climate change versus energy sources. And if you have more questions at that time, you can answer it. But thank you so much, Kevin, and thank you, everybody. I think we're finished today.